Okay, so I forgot to I'll deal with that later. All right, so today is the Project 6 kickoff. Final project, and I think, do I want to do this next week or Thursday? I think Thursday I'll kind of throw an example final exam at you, and that example final exam will operate on a completed P5. So to experience the stress and misery of a final exam, you'll want to come on Thursday. And who wouldn't want to? Yes, sir.
The final exam also operates on a completed P5 as well, right?
Yes, so that's exactly correct. The final exam the actual final exam will be on P5. Yep. So you'll definitely want to have P5 working prior to 2 weeks from now. Project 6. 3 things to do: initialization and termination blocks, near and touches, and animation blocks. Initialization and termination blocks, as a reminder, what do I have in here? Yeah. All right, so we have these event blocks that you would have gotten going for previously. Hopefully those are all working now for P5, where you have various events, mouse down, keystrokes, and it'll run code. The 2 being added to that is that just prior to your program running, it will run any initialization blocks. So just like the other event blocks, you can have more than one initialization and more than one termination. It just simply runs them in order. It'd run this one and then this one. And likewise, same thing with the termination blocks, which are run just prior to your program exiting. So for example, your exit statement, which ends the program prior to the person hitting Q, it would run just prior to you exiting. You should be ensuring that all the termination blocks are being run. The implementation of this is really straightforward. If you recall, there were 26 possible events, quote, keystrokes that you could receive, and 2 of those are initialization and termination. So you basically just have to have support for those 2 added, and you're good to go. So that won't take long. Near and touches are also fairly straightforward. These are operators in the same sense that addition and multiplication are operators. They're binary. If you recall, you have game objects like a triangle and a circle, and you can say if my triangle is near my circle, then you'll take some action. What kind of thing will these return? If I do, let's see if I have that here. So if I have a triangle, try, and a rectangle rect, and so what is the result of this operation? Yep. So again, when you're creating operators, the 2 key functions you have to write is you have to write a type function and an evaluate function. The type function is int, right? The type function is always the kind of thing that is the result of the expression. As far as evaluate works, here you are actually working with game objects. So in all of your other evaluate, you have things like stuff. And we had, what do we have? Constant, we had a right-hand side, something like this. And we would get it, and then we would get it as int, as double. So here you're going to have an as game object that you would have inside this function. And then these game objects have a near and, I guess this would probably be like left-hand side, right-hand side. So that these game objects already have near and touches functionality in it as member functions, and you just call it with this kind of convention, and it'll give you a true or false, and you can build your constant integer 0 or 1, and you're off to the races. So that won't take too long. The one that is going to take the longest to implement are the animation blocks. If I look at my code here. All right. So recall that an animation block is a block of code. So here is a block of code that does some sort of algorithmic thing on your variables in your application. And this block then I attach to game objects. So this specific animation block is intended to work with a triangle, and it's called dance here. So here I have where do I have a triangle? Yeah, pyramid is a triangle, and it has an attribute. All the attributes we've dealt with now have been either integers, doubles, or strings, such as x here. The animation block attribute is the only one that is not an integer, double, or string. It is an animation block. Okay? And to begin understanding the functionality that you're going to have to put in place to support animation blocks, it is nice to look at a C++ phenomenon. So here what I have is I have 4 function prototypes, atom plus 5, atom plus 6, and so forth. And here's a definition for one of those functions. Takes 2 arguments. In this case, since it's, this should say, yeah, that's fine. It adds them together, and it adds 5 to it. So to be sure, the function is nonsense and simple, but it works for what I want to show off here. And then here's a main function where we're actually calling this function here and calling atom plus 6. Talk about that in a minute. All right. So it is legal in C and C++, it is legal to have a function definition prior to the use of the function, and that we see here. We have the definition of the function on line 6 and 7, and then we're using the function on line 11. That is perfectly legal in the language. I don't think that is a surprise to anyone. It is also legal for me to take lines 6 through 7 and move them to after the main function. That is legal only if we have provided a prototype prior to our use of it. So as long as we have a prototype, then we can use it, and this can follow afterwards. It is legal for us to omit the variable name in declaration/prototype. So you'll note here, nowhere do I have first or second. I would say much of the time it is nice to have those variable names in here for the purpose of readability for someone using this stuff. Particularly you have some sort of software engineer coming along 6 months later. What software engineers don't tend to like 6 months later is variable names that look like this that are abstracted and don't have any context. So normally you'll have something, and even first and second I don't think is very conducive. For me, I don't know, first operand, second operand. These aren't good function examples anyway. But anyway, I'm rambling. The point is that the presence of variable names in function prototypes is for the benefit of us humans. The compiler does not care. The compiler ignores that information. It's not relevant. The only reason we have a prototype is to tell the compiler the proper use of atom plus 5, which is what the function returns, the name of the function, how many, and the kinds of arguments. That is sufficient information for me to use it correctly here, or for the compiler to let us know if we use it incorrectly, right? Nowhere is the variable name relevant to what the compiler needs. So that's what this is referring to, legal to omit variable names and declarations/prototypes. And also, it is legal to have function declarations/prototypes. For functions, for which, this is all horribly worded. Oh well, I'm going to leave it. For example, here I have a function prototype for atom plus 7, but if I search this code, nowhere do I use it. That is perfectly fine. There's nothing wrong with having a prototype for a function that you don't use. We don't think about it, but we actually exercise this phenomenon daily when we're coding. When you pound include IOStream, you are including prototypes and definitions for a whole slew of functionality for doing input and output in the language. You are not exercising every last piece of input and output functionality when you create your Hello World program, right? So that there is an example of including a bunch of stuff that you're under no obligation to use. Again, this is just information for the compiler should you decide to use it to ensure that you're using it correctly. All right. All of these things have parallels in GPL. So looking back at this example, let me look at these. It's legal to have a function definition prior to use of a function. It is legal to have an animation block prior to the use of that animation block. Now here, the word use has a slightly different context. To use it is to basically assign it to something. So here I'm defining it. And then here I'm using it. I'm assigning it to the animation block attribute of some existing variable. When I hit A key, I go ahead and do that assignment. This is effectively using the function. So that's what that's referring to. It's legal to have the function definition follow its use as long as there is a prototype prior to it. So what I can do is I can take this animation block and I can move it down here. So now the definition is following my use of it here as long as I've got a prototype. And in GPL, the prototype is the keyword forward and then the information for that animation block. So looking at keywords for a moment, if I look at line 42, animation is just a keyword to specify the kind of block that you're about to define there. So that's a keyword. Dance is the name of the function. And then these animation blocks, they're kind of like functions, except they only take a single argument and it's a game object. So triangle try there. In this case here, we have the keyword forward to say we have a prototype essentially coming, the keyword animation, the name of the function, and then the kind of thing. So that is the equivalent of a function prototype, and its presence allows us to put the actual animation block after, right here. The animation block is coming after its use here because of the prototype here. So that's what the second one is. It's legal for declarations to omit the variable name. You'll note that in none of these examples here have I done that. It's fine to put it in there, but your parser should just ignore it. The parser doesn't care whether it's present or absent. You don't use it. And then finally, it's legal to have prototypes that are never used. And then this example is, I've got prance, twirl, and squirrel here as forward declarations, and nowhere in this code am I actually defining a prance, twirl, or squirrel animation block. I just have dance. So those are all the parallels with the languages that we know that we have to go ahead and mimic in GPL. There are two different kinds of things when you're dealing with animation blocks that you'll find. One, and they're called animation block and animation code. And it's a little bit confusing. Why are there these two different things? And I can explain that by looking at C++ again. So I'm gonna do a little bit of pseudocode. Animation blocks are a lot like function pointers. So I can create a function pointer. Again, this is just pseudocode for So it is legal for me, these are function pointers, and this is just fine. I can create it as a pointer variable. I can assign the address to one of these. I can also create another function pointer. All of these things I would refer to as simply function pointers. However, there is one bit of code that is illegal to do, and that's represented on this line here. Atom plus 5 is an actual function. So if I write atom plus 5 here, whether I have that there or not, doesn't matter. When I look at it on line 6, if I write atom plus 5 and I don't have the parentheses here, that is considered a pointer to the function. I can go ahead and assign that to a pointer variable as I've done to line 6. However, I can't take it and assign something to it. So writing it without the parentheses makes it a pointer, but it's a read-only pointer, right? It's a non-modifiable pointer. Does this make sense? I can't change what I'm defining on line 16. That is an actual function. I can't assign something to it. It won't even compile. All right. This is the distinction between animation block and animation code. Animation block is like your function pointer, and whenever you refer to them, it's like referring to just an animation block. However, the actual block that you define, you can't assign to. That's referred to as an animation code. So, looking back here, I can take an actual, this would be considered an animation block being assigned to an attribute. These two are both legal, but it would be illegal for me to do something like that because I can't actually change dance. So in this context, dance is the animation code, the unchangeable pointer. Everything else you just call an animation block. So that's kind of the parallel between C and C++ and what we have here. And that's why the two are distinguished in GPL. Animation code is the actual block of code. Everything else is just a pointer, essentially. All right. Let's see, was there anything else? Yeah, okay, so I was talking about that there. The near and touches, you get rid of that pretty quick. We have some interesting things happening with symbol tables now. And the first thing to look at is when you're parsing. This is probably a better example to look at. You're not running your program, you're just simply parsing. And when you're parsing, if I have line 49, let's say that's up near the top of my GPL program. In order for line 49 to parse correctly, Y has to previously have been declared, and Y has to be in the symbol table, right? Otherwise, you generate a not declared error, and you'll never run your program. All right. Imagine when you're parsing this then. That means that all of these lines right here, try needs to actually exist in order for you to parse this successfully, or you're going to get undeclared errors. And additionally, I could have had a variable double try. That's fine as well, right? There's no conflict here. If you think in C++ terms, 42 is a global variable, and the try being declared on line 43 is just local to the function. And there's no problem with that. So this is where in Project 2, we set up this whole architecture to be able to have multiple symbol tables, but we've never done that. We've always just had the global symbol table. This is the point in time where we can have multiple symbol tables. So what will happen is while you're parsing, as soon as you hit this point in parsing, you have to create another symbol table, put it on the stack of symbol tables, and then you declare try as a triangle and put it on that symbol table so that all of this here will parse. And whenever you ask for the variable try, it will get the topmost try that it finds. And if I say XYZ, it'll look for XYZ in that topmost table. It won't find it, so then it'll go down to the global symbol table and look there. If you've coded everything from Project 2 correctly, this should all work, no problem. Some of you will have problems. Just keep it in the back of your head that a possible place for you to look is that you just have a bug from Project 2, and you're only seeing it now because this is the first time you're exercising that functionality of having more than one symbol table. So again, when you parse, when you start parsing this stuff, and it's all in the write-up, you'll add another symbol table, parse, parse, parse. As soon as you finish parsing this, you'll go ahead and remove the symbol table. Interestingly, this will happen when your program's running as well. When your program's running, if this dance animation block is attached to pointy hat, several times a second, pointy hat is going to execute the code of its animation block. And every time it executes the code of its animation block, you're going to have to add another symbol table, declare try, run this code, and then when it's done running the code, you remove that symbol table. Another interesting thing to note is that where C and C++ have value semantics, meaning that function arguments are copies, we have reference semantics in GPL. So here, when the animation block on line 43 is executed for pointy hat, try is nothing more than a reference to pointy hat, meaning anything I do to try in this function, I'm actually doing to pointy hat. Okay, and then also to pyramid for that matter. It depends which one's calling this function. So our idea of a symbol gets more complex as well. We're going to actually derive a class off of the symbol class, and it'll be called a reference. And the reference will be exactly as I said. It won't be its own symbol. It'll merely be referring to an existing symbol. So we'll have that happening in this project. And I would say that that is about, oh, I guess one other thing to talk about is the idea of declaring these. Remember, we're under no obligation to use these if we have these forward declarations. However, they do pollute our symbol table, our global symbol table, because for me to have this here, this forward declaration, allows me, oops, I have it twice, For me to have this forward declaration for dance allows me to use it right here. Well, for me to use it, it has to exist, which means the forward declaration has to put an entry for dance in the symbol table. It's just stubbed out because we don't know what the code is for it yet, right? Later on, when you get down to actually writing the animation block, then this will generate, write a block of code. It's just a statement pointer to a linked list of statements. You'll have to take that statement pointer and go ahead and change the symbol that's in there for dance to add that pointer. Anyway, what that means for prance, twirl, and squirrel is those will be 3 additional entries in your symbol table that are never used in your application. So just before you run the application, you need to remove these from the symbol table so that they don't pollute it. Now you may say, well, is it really doing any harm for them to be there if you're not using them? And the answer is just do what I say. No, it's that.
Increasing the size of the binary.
Well, yeah, I mean, it increases a little overhead. Certainly every search you do in the symbol table has now got to contend with these extra symbols. Also, recall that when you run a program, before you run it, you get a dump of the symbol table, and after you run it, you get a dump of the symbol table, and you will have these entries in there, and you don't want them in there if they're not being used. So just before you run your program, you have to go through your symbol table and remove these things. And the mechanism that is used for doing that is sets. So if I look for, I think defined will help me. We have 3 sets, and these sets are all just strings. It's a string of symbols that have been declared. That would be these forward declarations. There would be a set containing a list of strings for the symbols that have been defined. In this case, in my example, there's just the one for this code here. And then this will be a set of strings for the symbols that have been used. And note, this is all for animation blocks. This is all specific to animation blocks. So these 3 sets, and then again, used means that you're actually putting it to use, assigning it to the animation block of the game object. The reason for these sets is, one, so that you can do cleanup. What you do is you take everything that you've declared. So I've taken everything I've declared. I subtract from it the set of things that are being used. So if I take these 4 and I subtract dance from it, because dance is the only one that I'm using, then I'm left with these 3. So that's doing a little set arithmetic gives me the names of the symbols I need to remove from the symbol table. It also does error handling for us. So we have an error if I have, say, lines 24 and 29, where I have the forward declaration and I use it, but then I never actually define it, right? So this is a not defined error if I don't actually have this code here. And so again, you do a set subtraction, taking all of the things that are used and all of the things that are defined, and the difference between those is going to tell you the things you're using that you didn't define. And you generate errors, and then your program won't run. So all that kind of stuff it's all described in here, of course, and it's used with these sets. I say it explicitly in here, but let me repeat it because I feel it's pretty important. I think a lot of us are comfortable with sets and set subtraction and so forth. I think very few of us have actually used it in C++, and C++ is horrendously unintuitive on how it deals with sets. So what you're encouraged to do is when you reach this portion of the project, set your project aside, create a simple C++ program, and play around with the sets. Create 2 or 3 sets full of strings, subtract some from another, make sure you understand how they work, how to use them. It is unintuitive, it is funky in C++. You do not want to do that experimentation with this huge project. It'll just make debugging a nightmare. Okay? So that's my folksy wisdom for today. And I think that is about it. Yep, the final, the most important and best step of the entire semester comes number 20, number 30, number 35. At the beginning of the semester, you wrote a game. You get to test your game on your own interpreter, right? So that is the final step to see that your game works in all its glory. All right, any questions? Okay, so then I'll cut you loose a little bit early to get going on this. As I said, on Thursday, we'll do a dry run of a final exam with your working Project 5. It'll include directions on how to make a copy of Project 5 so you don't destroy your working Project 5. And then into next week, we'll be able to support you on finishing up Project 6. Okay? All right, we will see you on Thursday.